Good afternoon. My name is Mike Voss, and I'm going to be talking about threading building blocks and features that we have added in the past or are currently working on that help tune your applications that are using TBB for non-uniform memory access architectures. So the outline of the talk is I'm going to give a brief overview of TBB for those who are unaware of what TBB is. Then I'm going to talk about the intersection of TBB, non-uniform memory access architectures, and composability, and that's really the challenge in dealing with NUMA architectures and TBB is maintaining composability while tuning for NUMA. I'll then talk about existing features that are already there in the library today that you can use for NUMA, and then I'll talk a little bit about some planned features that should be available soon, and then I'll give a short case study of using these new features for NUMA tuning in the OpenVINO toolkit. Then I'll make some conclusions. So TBB is a portable C++ library for threading. It's available as an open source project, and it's also commercially supported by Intel. It's available for, the benefit is that you can write your application using these high-level algorithms, and then you can use it across multiple platforms. So it's supported on a number of different OSs like Linux, Mac OS, Android, Windows, and more. You can learn more about it at threadingbuildingblocks.org, or there's a recently published book, of which I'm a co-author, that is available for free digitally, or you can order a copy. So TBB is a collection of building blocks that can be used to create scalable threaded applications. And it's a C++ library. So it has high-level parallel execution interfaces like parallel loops, pipelines, task groups, and a flow graph API which lets you express data flow and dependency graphs. There are some controls for controlling the execution of those high-level execution interfaces. They're all executing on top of TBB tasks, which are scheduled by the TBB work stealing task scheduler. And there's some really good properties about this work stealing task scheduler that are good for composability. And I'll get into those in more detail because they come into they affect how you can tune for NUMA. There's also other things in TBB like generic concurrent containers, like hash tables, queues, and vectors. There's a scalable memory allocator. These things are independent of tasks and this task scheduler, so you could use those even in an application that just uses native threads or OpenMP. So there's really these two or multiple separated, you can see the relationships here. So you can use your containers, you can use the memory allocators, you can use the execution interfaces. You can really pick and choose what's useful for you for your application. So since we're at an HPC conference, I'll be a little defensive and answer the question that may be in some people's minds, which is, why not just use OpenMP? Why use TBB at all? Why are you even here at this conference talking about TBB? So I've worked on OpenMP in the past, so I'm defensive in both directions. I'm defensive of OpenMP and TBB. And so I will say that if you have an OpenMP application that works really well, there's no need to switch to TBB. If you're happy with OpenMP, it's giving you everything, just use that. But there are cases where TBB has advantages over OpenMP, even in high-performance applications. And some of these advantages can be, and they're dependent upon the application characteristics you have. One is TBB is a C++ library. So it has a more natural C++ interface. So if you like C++, TBB you'll feel comfortable with. The second thing is it offers better composability. So TBB is designed from the bottom up for composability. It has a single shared thread pool. You can express parallelism using tasks. You can nest parallelism. You can have concurrent parallelism. You can have sequential regions of parallelism, and they're all using the same limited set of threads. And so this means that you're not going to oversubscribe your system if you write complicated applications, even if the nesting is in library calls that you're making. And this is all enabled through its work stealing task scheduler. This is going to come back, though, when we're talking about NUMA, because some of these advantages of TBB you have to restrict if you want to do tight tuning of the library, and there's a trade-off to be made. So there are examples of applications that are all about performance, high performance, that actually started using OpenMP and at some point switched to TBB for performance reasons. So this is not an insane thought that TBB for HPC can offer better performance than OpenMP. Examples are Intel has an implementation of Stack A2 benchmark, which is a finance benchmark that's used in risk analysis. And it started with OpenMP as the way to do threading, but because of the complex nature of the benchmark and nested parallelism, they moved to TBB to get better performance. Similarly, at the end, I'll talk about the OpenVINO toolkit, which is for computer vision inferencing at the edge. Similarly, they started with OpenMP as their CPU backend and moved to TBB because it worked better because of composability in complex pipelines. So, since I'm focusing on non-uniform memory access architectures and execution and tuning execution, I'm really going to be focusing on just the execution components of TBB, so the parts that are in gray here. Before we can get into how we're restricting TBB, I want to take a minute to just talk about how TBB works in the first place. So we'll look at one of the algorithms, a simple parallel for loop, and I'll talk about how actually this works with TBB. So here we have a parallel for. It's a very naive matrix multiplication that's here. And this is an example of a TBB algorithm. So you pass into it something like a range from 0 to m, that's your iteration space, and then you have a C++ lambda expression. And so what you're asking is you want a parallel execution of this. The range is 0 to m, and for each index in the range, you want to apply this lambda expression. And together, that index and that function, that's your task. So what actually happens in TBB, unlike OpenMP? So if you had OpenMP, what you do for a parallel loop, you'd assume if I had 2 threads, I get immediately 2 chunks of work, the left half, the right half, the threads execute those. So in TBB, things happen differently. So you start with a single task that represents, at the top, it's called T0 here. You have a single task that represents the entire iteration space. And thread 1 has this. This is the initiating thread. And it looks at this range and it sees it's too big based on some partitioning strategy. And so it decides it needs to break this to create parallelism. So it creates a left and right half, creates 2 new tasks, T1 and T2. It's going to keep one of those tasks and I'll make another one available for stealing. And it will continue to do this. So it goes down to T1, then T3, then T7, and eventually it reaches a size of a task that it feels comfortable with based on this partitioning strategy, executes that as a task. Meanwhile, if there are other threads in the system, the threads can come in and steal away some of these other tasks. The thread 2 might come in and steal away T2 and repeat that process of subdividing until it finds that it's comfortable with the size of the task and executes it. At the bottom, there's a timeline where these 2 threads are making their decisions. And here, 0 represents task 0, so thread initially is task 0. It creates 2 subtasks. It pops one for itself. There's an idle thread, thread 2. It has nothing to do, so it randomly looks for a victim thread, finds thread 1 has some work in its double-ended queue, and steals away one of those tasks, T2. The good properties of work stealing as implemented in TBB, as you can see, there's only that one steal because it's thread 2 stole the oldest thing that T1 created, which represents that really big piece of work. If there are other threads that come in and become involved, they might steal task T4 or T6. And these have really good properties for composability because there's no assumption about how many threads are participating. If only thread 1 was there, eventually it would execute the whole thing itself. And this is great for composability, but it causes problems when you're doing things that depend upon first touch or next touch, or you want to really control where tasks execute. And that's what the rest of this talk is about. So composability, I've mentioned a number of times. Composability is a measure of how well a parallel model performs when components that use it are composed together. So if you have a TBB parallel algorithm that another one's nested inside of is an example. The dynamic nature of TBB that I showed on the previous slide is great for composability because there's not assumptions of how many threads are participating. Idle threads can steal work. If thread 1 was executing on or thread 2 is executing on a more loaded resource, thread 1 can steal back some work from thread 2. So there's all these good properties. And because of them, there's an increase in performance in many real-world applications like StackA2, like OpenVINO. But the thing that I'm faced with time and time again is we get some HPC customers who have a very simple micro benchmark or a flat application, and they're like, this performs a lot worse. TBB performs worse than OpenMP because OpenMP has this, by default, more static chunking than TBB. So it's not for free. In some cases, in micro benchmarks, you might see the overhead of composability. But in real-world applications, it often outperforms something that's more static. But this brings us to the big problem. Now we have NUMA architectures. So a uniform memory access architecture, all your cores have uniform memory access to all of the shared memory. A non-uniform memory access architecture, some cores that are physically closer to some regions of memory than others. So if they need to, for example, a core in NUMA node 0 needs to access memory that's in NUMA node 1, it has a higher latency to get that memory. So now we're looking back at TBB without controlling anything. We have 4 threads that participate in this loop that we looked at before, and let's assume that this iteration space is really large and it's accessing some memory, some array, and the left half has been allocated in NUMA node 0, the right half in NUMA node 1. And now TBB is doing its really smart composable thing where it's just stealing work to balance load. We could have a situation where thread 1 winds up executing the leftmost quarter, thread 4 the second quarter, thread 2 the third quarter, and thread 3 the fourth quarter. And we get this behavior now where because we didn't control anything, thread 1's accessing local things, thread 2 is doing remote memory accesses, thread 3 is doing local, and thread 4 is doing remote. So how do we fix this problem? There are features already in TBB that let you control execution. These include partitioners and scheduler controls. So I'm going to talk about some things that already exist. One thing is if you are depending upon first or next touch policies, we do have something called an affinity partitioner. And it doesn't tightly control what TBB is doing in terms of deciding how big chunks are or which thread executes which chunk. But what it does is it remembers from one execution what the scheduler did, and it provides hints in the next execution that make that pattern more likely to reoccur. So you can create a affinity partitioner object, AP here. Then if you have 2 consecutive loops that you want the same stealing behavior to happen in, you just pass in this object. TBB is allowed to still do the stealing, but it's given hints that push tasks to certain threads. So before they steal, they'll say, oh, maybe I'll do this one instead of randomly stealing. So you can recreate a pattern of execution. And if we were looking on a scale of composable to not composable, this is pretty composable because it's a hint, and you haven't done anything to say, put this task on this core. You're just saying, remember what you did, and try to recreate that kind of scheduling again. This can help with locality and locality on NUMA architectures. You can even be more restrictive and try to get something more like OpenMP. So OpenMP, by default, would create uniform sized chunks for each thread, and each thread in consecutive loops will execute the same chunk. So in TBB, you can mimic this behavior by using a static partitioner. Here you don't need to create an object because you're just saying create 1 chunk per participating thread and push the chunk to that thread. So if you have 2 consecutive loops and they both use a static partitioner, the threads are likely to get the same chunks. So you get that same kind of static behavior that OpenMP would have. It doesn't actually completely turn off stealing, but you've created huge chunks. So for one thread to have to steal, there'd have to be a huge imbalance, or that thread is extremely slow. It never got its chunk initially. What we've chosen to do here, though, is maximize chunk size, which sort of takes away some of the composability of TBB because we've limited opportunities for stealing, and that was part of the goodness of TBB in the first place. But it's something you can do if in some part of your application you really need this kind of behavior. Okay, so one other thing we can do when we're talking about NUMA is in TBB is we can create isolated groups of threads. So let's say now you want to create 2 sets of threads because you know you have 2 NUMA nodes, each with 2 cores. You can create what's called a task arena. And you can say how many slots for threads are in it. So you could create on this platform 2 task arenas, each with 2 slots, using this interface here. And then you can explicitly put work into one arena or the other. When work arrives in an arena, some threads from that shared thread pool that TBB has will migrate into that arena. And any work that happens in that arena will stay in that arena. Any threads in the other arena will not be able to steal work away from that arena. So you've isolated the work. Those 2 threads are now working on that work that you've wanted to isolate from the other work. This is somewhat composable because there's still stealing going on, but you've created this boundary between these isolated groups of threads. But this gets you only partially there because we didn't do anything to actually pin threads yet. TBB by default doesn't pin threads to cores. It allows the OS to move threads around. This is part of, again, being composable. But there is an interface if you really want to bend things still and make it more static, you can do that with TBB. But again, you're taking away a little bit of its flexibility and composability. So there is an interface called Task Scheduler Observers. You can create and associate with an arena. And then each time a thread from that shared thread pool migrates into your isolated group, you get a callback, and you can do whatever you want. So one thing you can do is pin it. So anytime a thread enters arena 0, you can say, this is one of my arena 0 workers. So in my callback, I'm going to bind it to NUMA node 0. Now when you enqueue work to the threads in arena 0, you know not only that they're isolated from things in arena 1, but any thread in that arena is bound to NUMA node 0. So you can create these things, but it's all a pretty manual process with these interfaces. And that's what the future is for TBB. In a very near release, you're going to see interfaces like this, where TBB is going to provide information about the topology. So you can check to see, well, how many NUMA nodes do I have in my system? There's also going to be interfaces for task arenas, where you can initialize. So here we have a vector of task arenas, and we create 1 per NUMA node, and we know how many NUMA nodes we have because of this info interface. And then we can execute work in the arenas, but before that, we can initialize them with a constraint. So we say arena J, all the threads that are in arena J will be bound to NUMA node J. So all of those things that we had to do manually with TBB before, there's going to be a more user-friendly interface for doing that. And there's a warning at the bottom. This hasn't been released yet, so it's very likely to happen. But it's not released, so who knows, right? Anything could happen. So now I just want to briefly talk about a good example, I think, of a case where, so Intel OpenVINO Toolkit enables deep learning inference at the edge. And it's a toolkit that supports heterogeneous execution across multiple devices like CPUs, GPUs, the Movidius Neural Compute Stick, and FPGAs. Earlier versions of the CPU backend used OpenMP, but they found that TBB, when they started using it in more complex pipelines, that TBB was more composable and could get up to 2x performance over OpenMP because of its composability. But what they saw also was that for some simpler benchmarks, it performed much worse than OpenMP. And that was because TBB was still doing this dynamic work stealing, and we weren't getting those repeated patterns of execution that did well for locality. So working with the OpenVINO team, is where we came up with this, with the more user-friendly interface. So here are just two results for two models from the MLPerf inference benchmark executed on a Xeon platform with two processors, total of four NUMA nodes. And what we see here is the relative performance to the best performing OpenMP backend for OpenVINO. And the leftmost blue bar represents not doing any tuning for TBB and NUMA. And you could see for ResNet, we were seeing only 50% of the performance of OpenMP. And for MobileNet, we were seeing only 75% of the performance of OpenMP. Now remember, OpenVINO wants to use TBB because for their real-world applications where they're complicated, TBB could give 2x performance, but they had to deal with this as well. And so, using the manual interfaces provided by TBB, those task arenas, the task scheduler observers, they could get very close to OpenMP performance. But as a lot of manual tuning, well, at least verbose code, using the simplified interface, they were also get much closer to OpenMP performance. So that's that new interface that I was providing earlier. So in conclusion, TBB, which was part of oneAPI, so we're calling it now oneTBB. oneTBB has, or the Intel version of TBB is called oneTBB, has features that can be currently used to tune for NUMA. Restricting the scheduler can sacrifice composability, but you can do it if you're tuning for locality. I showed examples of affinity partitioner, static partitioner, task arenas, task scheduler observers, how they can be used to tune TBB performance. I showed some future features that simplify that process, and I showed that we can get better performance on some real-world applications that are sensitive to NUMA effects by using those features. So another push for the TBB book. A lot of the samples that I showed here, or samples very similar to them, are available in the book. So, and again, there's a free digital copy if you want to download and look at those. There's also the source code for the book is available at GitHub for all the examples, so you can look there. And so all of the examples that I showed, there's something similar to it that's available in the book.